I don't know how much discussion is actually happening about any of these items in particular. So let's see. Does anybody want to offer what they think is true or false of the first question? A big theta bound will exist for every function. True or false? False? Great. Anybody want to tell me a situation in which the big theta doesn't exist? To the front row, yeah. Yes, when the simplified tight big O is not the same as the simplified tight omega, that means that the tightest upper bound and the tightest lower bound are different. And in that scenario, theta does not exist. Questions on that one? Cool, so this, we'll just say, are you gonna let me? Are you gonna? Maybe? Oh, did you freeze? You froze. Okay. The second question, as I restart PowerPoint, one possible best case for adding to array deck is when it is empty. This one is one of those annoying situations where you have to kind of figure out whether or not this is true based on the definition of what a best case could be. So, do we agree? True or false, one possible best case for adding to array deck is when it is empty. Any suggestions as I restart PowerPoint? That's what I sort of expected. So maybe a better question to ask then is, would we consider adding when something is empty? Does that technically count in our like case analysis? Does that count as a best case scenario? I like where you're thinking, yes, like it matters if we're like, adding to the end, to the beginning, things like that. But to take it to an annoying meta level, when we're talking about case analysis, the current state of the data structure, that's not really a case. A case is more like what's going to happen in practicality that may or may not create a situation in which this code's performance is different from another portion of the code's performance. So when the data structure is empty and then becomes, not empty, meaning when you add the first thing, that's not really a case because that's going to happen in all scenarios, we're hoping, right? Like that at some point you will add. So that's not a case that would require its own separate code model because that's just one of the steps that's likely going to happen in any scenario in which we're using array deck, that at some point it will go from empty to not empty. Clarifying questions on that? It's not a separate case because the code is always going to probably encounter that. We're talking about case analysis from like what's happening in the reality of the world such that it might exercise the code in a unique way. Yes, question.
So then the answer would be by technicality, yes, or true or false?
So by technicality, the answer is false. That is not true because when the array deck is empty is not a best case. We can't call when the thing is empty a case for separate analysis and separate code modeling and then separate asymptotic analysis. Yeah? Don't worry, we're going to keep hitting on these distinctions between best case, worst case, and what that means. Okay, let's see. Will you let me write? Haha, false. Okay, false. Okay. We only use big omega for worst case analysis. True or false? Okay, good. I'm glad. Yes, false. False for that one. Now I understand it's very easy to mix up these things. Big O is the upper bound of the growth rate of the runtime, which means sort of like what's the fastest the runtime can increase, i.e. what is the slowest the code can take to run. That's what we mean when we mean that upper bound, right? So it might seem like Big O is analyzing like how bad can this code end up performing, but asymptotic analysis can be applied to any code model. The case analysis comes before the asymptotic analysis. So a case analysis might be the thing we're looking for is always in the list versus the thing we're looking for is never in the list. Those are two separate things. They might exercise different bits of code, thus they might have different code models, and you can apply asymptotic analysis on both of those, where maybe in one of those situations, it's big O is constant, and in another situation, it's big O is linear. So we're using big O for both the best and the worst. We can use big omega and big theta in the same way for both the best and worst case scenarios. So I agree, this is also false. Any questions on that one? Okay, then if a function is in O of n squared, it can't also be in omega of n squared. It can only be in one. True or false? False. Yes, I agree. Good job, everybody. Remember, if something's simplified tight upper bound is the same of its simplified tight lower bound, can we tell what the theta is? Yes. What is the theta of a function for which this could be true? I agree. Yes, theta of n squared, which could be any function that has some constant c, n squared, plus some, I don't know, other constants. Something like that. Anything in that category. So all of these are false. Any questions? Okay. I expect this to be confusing. That's why I put these on this slide. If you're still not clear, don't worry. We're all in this together. We'll continue to iterate on it. Announcements, the usual. You've officially got Project 1 out. That is due on Wednesday. You've got Exercise 1 out. That is due on Friday. Does anybody have any administrative questions? Cool. Yay. All right. Okay, great. Because we have a delightful amount of stuff to get through today. In fact, I will tell you that this lecture historically used to be 3 lectures, and then the most recent time I taught it, it was 2 lectures, and then this quarter I decided, screw it, we're doing it in 1. Yeah? Here's the method to that madness, y'all. What I am about to talk about today is how to do this entire pipeline that we've been talking about, but specifically in terms of recursive code. Up until now, everything we've written models for has been loops or method calls or procedural type code that it's a little easier for our brains to sort of follow linearly. Now I'm going to talk about it in terms of recursive code. And when I first taught this class, I spent a whole week on it, and I made you do a bunch of math on the midterm that involved like finding closed form for recurrences and doing a bunch of summation identities. And then as we've gone on, I'm like, maybe I just talked to you about the theory and I never actually put any of this sort of math on a test. So we are going to go whirlwind through this, but that is because I am intentionally not going to ask you to do the same math on a midterm that I used to in this course. So I'm going to try my best to change how I teach this to give you the high levels, but I just want you to know that's why these slides might feel very detailed and intimidating, because once upon a time I did make you do this, but not this quarter. Yeah? So, like I mentioned, we are working our way through this delightful code analysis roadmap, where we start with code, right? That's where we go. And then we go into case analysis. And then from case analysis, we go to asymptotic analysis. And so what we've got here, right, is we've got, as you can see, we've got some code that loops from 0 to n. So we've got a loop that runs in n time. And then we've got some amount of checking here that's like maybe like this is an instruction, this is an instruction, this is an instruction, I don't know, things like that. So that's maybe where that 3 comes from. And then, no, don't do that. Then we've got this return -1 at the end. So what this code is, this is linear search. So if the thing that I am looking for always happens to be the very first thing in the list, I end up with just this sort of singular, check here and then return. And so I end up with some sort of constant time function. Now, the reason this is the best case is because I'm not putting any limitations on how many things are in the collection, meaning I can still create a code model that tends out to infinity. So if the thing that I'm looking for is the first thing in the list, it doesn't matter if there's 2 things in the list or there's a billion things in the list, right? I'm always going to have this sort of constant time lookup because it just so happens that the thing I'm looking for is always at the front. Very different from the scenario where the thing I'm looking for is never in the list, meaning I got to start at the beginning, I got to look all the way to the end to ensure the thing I'm looking for isn't in the list. So the best case is like find it right away. And then the worst case is like no find. So both of these can create a code model that tends to infinity, that can graph as we increase n. So as you can imagine, when we don't find it, if we have to look through the 5 things in the list when the n is 5, that takes us 5 iterations. If there's 500, that takes us 500 loops, so on and so forth. So here's where we get that 3n plus 1. That 3 is maybe coming from here, like I mentioned. That plus 1 is maybe coming from here. And so we've got 2 separate code models now. F of n equals 2, f of n equals 3n plus 1. And then once we've got our code model, then we move on to our final round of analysis, and we can do asymptotic analysis on both those separate code models. So in this case, it's constant. So it's a theta is also 1, or sorry, omega. There you go. Yeah. And then you can imagine that I could sort of like see how we've cleverly made these little puzzle pieces. I could like puzzle piece asymptotic analysis onto this worst case function as well, and we would end up with O of n, theta of n, omega of n in the worst case. Questions? So this is our complete roadmap for how to analyze code. Like I mentioned today, we're going to talk about how to analyze recursive code, because recursive code is a brain twister, a consciousness melter. I don't know what you want to talk about it, but people always ask me, what's the moment in computer science that really like is a make or break? And lots of instructors like to come for me and say that it's the x equals change x series, but I think that's disrespectful because I think y'all can crush that. I think it's recursion. So if you were that person in 143 when they first introduced recursion and you were like, wow, this is melting my brain and computer science no longer makes sense, guess what? You're not alone. I used to be 143 TA for like 9 quarters. Everybody feels that way, okay? The reason is because our brains can't really linearly follow recursive code in the same way that we can with loops. So when we're talking about creating these code models, it actually becomes also more complicated. But I'm hoping that walking you through this will also help you understand a little bit about the patterns that's happening in recursive code. You will find that recursion is really useful in certain scenarios, and those scenarios have pretty repeatable patterns. So we're going to talk about those patterns and how to analyze them. The 3 patterns we have is pattern 1. If I give you n items, at each recursive level, you half the items. So if I give you 10 items to analyze, then you make a recursive call on 5 items, and then on 2.5 items or 2 items, and then on 1 item. The second one is some amount of content size input, and then you do work. I'll talk about what that means. And then pattern 3 is doubling the input. So each recursive call has 2n, essentially. You will recognize all of these patterns when I actually get to the code, because you've probably encountered all of the code that I'm about to show you. So the first one, having the input, surprise, binary search. Binary search, if we need to dust off some cobwebs, is the look through the phone book algorithm or look through the dictionary. I've got like a big old thing, and I'm asking you to find one particular entry in a sorted set. So let's say you have a dictionary, you're trying to look up a word. Let's say your word is fun. I'm trying to think of something kind of not obvious. F, I would maybe go to my book and I would open up the very middle and I would say, okay, based on what's in the middle of the alphabet, which I don't know what letter is in the middle of the alphabet. If anybody does, I'm going to feel like it's like an I, H. Am I around the same area? You know what I'm talking about? I would go into my dictionary, I'd open it up in the middle, and I'd ask myself, is this point in the dictionary past the F's or earlier than the F's if I'm looking for the word fun. And then I would eliminate one half of the dictionary, and then I would jump to the half within that sub half, and then half and half again. I've got an animation on the next slide. But that's sort of what we're looking for with binary search, and you can see that in the code, where what we've got is we've got these 3 values, high, low, and then we're sort of looking between the high and low, and we're constantly adjusting to eliminate half of the possibilities. Like, oh, we know it comes before this, so we don't have to look in any of those later problems. Let's take a look at the actual animation. So let's say I have a list like this, and I am searching to see if this list has the value 42. Now notice, this algorithm, in order to work, must be sorted. But it's a great searching algorithm if you've got a sorted set of things. So if you've got a sorted set of things, what we do is we kind of start with these min, max, and middle values. And to start off with, we're looking at the entire set of stuff. And then what I'm going to do is I'm going to look at that midpoint just like I did in my dictionary. I'm going to ask myself, hey, does 42 come before 30 or after 30? Hopefully we can see that it comes after 30, which means I don't need to look at any of these numbers anymore. I know 42 is not going to be in that set, and I have just halved the amount of things I need to search through. Then I will update my mid to the middle part of this sort of subsection. And then I'm going to do that sort of analysis again, and I realize, hey, like 56, that's bigger than my number, so I can eliminate all of these things. So originally, you know, I had, 17 entries, right? And then I halved that so that I had, 17 minus 9, I guess, in that case, right? And then I halved that, and then I sort of like keep cutting it in half, cutting it in half. So that's where that cutting the amount of input in half behavior comes from, because the way that this code is implemented is if we come back to the code, you can see, right, we sort of check like, hey, if the thing at my current middle state is what I'm looking for, sweet, return. Otherwise, if the thing I'm looking for is less than, binary search and move that mid. So this is like the act of cutting in half, where I'm looking from, as you can see, instead of looking from low to high, I'm looking from mid to high. Versus in this situation, I'm looking from low to mid. So that's my act of cutting the inputs in half based on how I pass the ends into binary search. So in case analysis, what is the best case scenario? Think of that linear search. If in linear search is the first thing, what's the best case scenario in this? Yes. That the thing is in the middle of the array. Exactly. Wouldn't it be convenient if this thing was right in the middle? It was index 8. It was the first thing I looked at. I didn't even bother to recurse from there, right? As you can see, boom, that's where we get our constant time. We don't even call a recursive call. It's right away. Then, yes?
What if the length of array is a even number?
If the length of the array is an even number, then I think we just pick one side or the other of the median. It ends up sort of being, as long as it's consistent, it's okay. And since it's integer division, it is probably the earlier of the two. Yes. So then if this is the best case scenario, what is the worst case scenario? You want to finish us off? Yeah.
It's not in the array.
That the thing is not found. Exactly. Because I have to look through everything until I find it. Except in this very clever algorithm, do I actually have to look at every single item in order to determine that something's not in the list? No. At each level, I originally had a certain amount of things I had to investigate, and then I cut that in half, and then I cut that in half. And so the actual amount of things I've investigated is how many ever times I do that cut, and I check what's at the midpoint. So I will say take 30 seconds to talk those people around you. If we're cutting it in half and we don't have to look at every single thing, meaning it's not linear. Linear is meaning we have to look at every single thing. What do we think the big O of this worst case scenario is? Discuss. Go. Does anybody think they have it? Any groups think they got it? Raise your hand. Anybody else think they got it? I just want to see where we're at. That's not cool. Okay, fun. All right, let's see. Okay. Anybody want to share with us what they got? Yes, please. Log n. I agree. Anybody else have anything different? How many people got log n, perhaps? Yeah, I agree. That is the basis of this logarithmic time. And if it makes a little more sense, and I know logs were pretty foreign to me when I first started to have to deal with this, right? The runtime is changing rapidly down here, right? But then as the sort of like value of n's get greater and greater, we end up sort of like evening out. So log n inherently runs at, we'll say, or it grows at a slower rate than linear. So if that's linear, logarithmic might grow kind of fast, but then it sort of evens out over time. Anytime you have this sort of, I'm having the input, that is a common pattern for logarithmic growth. Here is a delightful amount of mathematical logic that you can read in order to be convinced of the thing that I just said. I am happy to walk through it with anybody, but like I said, I'm trying not to force y'all to have to do this math. Yes?
I'm guessing the answer is no, but what's the reason again for why the base of the log doesn't really matter in terms of big or notation?
Ooh, why doesn't the base of the log matter in big notation? So for context, you will see me write this all the time. And what I really mean is I mean this. And that's just in computer science. We are obsessed with log base 2 because we're obsessed with 2 based anything because we live in the binary. I know. But you're correct in that technically we infer this 2, but we actually do leave it as 2. We don't like change it and let it drop away because when we end up graphing the logarithmic growths, unlike the exponent, the logarithmic growths across each other, that constant ends up being negligible. So log base 3 looks almost identical to log base 2, log base 4, and so on. And the reason for that is some algebraic identities that I'm going to be real with y'all, I barely understand. But you don't have to either, necessarily. So binary search is in the logarithmic complexity class. Yeah? Now, that was an annoying approach because you were probably like, okay, Casey, we like kind of talked about it and we sort of like gut figured out this logarithmic growth, but that is not a sustainable solution in order to analyze recursive code. I was sort of like, we were trying to like intuit some patterns here. And so the reality is we need some other tools in order to actually produce a code model. But what we just did was technically we did our case analysis, right? Either it's found in the middle or it's not found. And then we were like, okay, well, in this case, it's constant. And then like our gut tells us this is logarithmic. And then that's where we get our asymptotic analysis off of those items. Let's introduce a mathematical tool now. So let's see. Oh, let's do some code modeling. That's what this is. Okay, so here's our binary search code again. So I'm pretty sure if I click through this, you can see pretty much everything here, right? All of this stuff, that's not recursive. Which is great because we're hopefully somewhat practiced with code modeling non-recursive code. And we're just directly counting the number of instructions. So up here, this 2 I'm guessing is coming from this, and then this, there's that 2, that 4, maybe here's 1, here's 1, here's 1, here's 1, something like that. Then here's a return. You'll find that I don't really care too much about these constants, but we can see in this collection of things, there's no factor of n. This is all just some amount of constant work. Here's some more constant work. I'm guessing that 6 comes from 1, 2, maybe 3, 4, 5, 6, something like that. But all of this, you know, some amount of constant work, right? But then we come down here, and one thing we haven't chatted about much is when we are code modeling other function calls, other method calls. The way that we do that is we would do the runtime analysis of the method call. And then if we say called that within a loop, we would multiply it by how many times the loop runs, or we would call it by how many times we trigger that method call. And so here that 2 is like, well, there's sort of like one method call here and one method call there. That's 2, but like they're recursive. So like, how do I know how many actual method calls are going to happen here, right? Like when we're looking at a loop, we see that loop start and loop end. So our human brains can look at like, okay, I can count exactly how many times this for loop is going to run. But in actuality, we can check how many of the extreme limit possible recursive calls there are going to be. We just usually don't talk about it in that way very often. We don't think about how many times we're going to have to recurse to get down to the bottom. And if you remember, the bottom of any recursion is the base case. And so we're going to call recursive methods until we trigger that base case. And so what we're doing today is we're trying to figure out this question mark piece here that's like, okay, well, how many times are we going to recurse? Because then I'm going to multiply that by however much constant work inside each of those times how many times I'm going to recurse. And that's what we're trying to figure out is how many recursive calls are we going to make before we get down to the base case. Don't worry, you're not expected to know that from this moment. I'm going to give you, yes, I'm going to give you a function for it. So meet the recurrence. This is a mathematical term. This is not a computer science term. And a recurrence is specifically this mathematical symbolism here that represents a function that calls itself. Get it? Recursive code can be modeled with a mathematical recurrence? Yeah. And so this is just some notation for you, but what we've got going on here now is you can see this like kind of looks like recursive code, and then it's got these sort of branches. And so this top branch, this is like the base case. And the base case, like we just saw on the previous slide, that's not the non-recursive part, right? And so hopefully we can apply those like count this many of instructions, right? Like that's this business here. It's when we get into the recursive stuff that things get really weird, but what we're going to do is we're not going to try to figure out that count. We're just going to use a mathematical expression to represent it, and then I'm going to show you a bunch of plug and chug stuff, which is the goodness. So here, this is our recursive case. And what you can see here is we usually, in this particular, we use T of n, and then what you can see is that T shows up again in the definition of the recurrence, just like recursive code has a method call on itself inside of it. The function has a reference to itself inside of the definition. So we make this little swoop-D. I actually don't know the name for the swoop-D, but I think swoop-D's cuter. And we have the base case. So that's however many computations are happening in the base case. Right now it's constant, like we just sort of saw. But there could be anything happening here that's non-recursive, right? This could be n squared. This could be n factorial. We don't know what you're doing in the base case, right? Totally independent. But then we need to indicate for what values of n that base case occurs, or what situation triggers the base case. Then we want to represent the recursive work in this way where we have a reference to T of n, but then we also need to include how n is changing. And if you think about writing recursive code, hopefully what you've got is you've got some input to the top level method call, and then you've got a base case that is triggered based on that input. And then whenever you make a recursive call, it should take your input from some state closer to the base case. So for example, if we have n is less than 3, n divided by 2 will continually take any value of n closer and closer to the base case, because it will continually reduce the value of n down and down and down until we ultimately hit the base case. If that's not what's happening in your recursive code, you're going to get an infinite loop. Otherwise, we're not going to travel from the top of the recursive stack down to the base case. So that's what we're really looking for, is we're looking for how does T of n come in, how is n changing? And then here's some, like, I don't know, this is some constant work that's happening inside of the recursive case. And then this here, this is the number of recursive calls. So this recurrence here, 5, that's apparently whatever we decided for this constant work up here. That 2, that's coming from the fact that there are 2 possible recursive calls. That n over 2, that's coming from this movement here where we are reducing the amount of n in which we are searching in half each time. And this plus 10, that's like the non-recursive constant work that's happening in that recursive case. Something like that. It's probably technically all of this stuff. Something like that. Questions on the pieces of the recurrence? We'll get plenty of practice. I will say, I'm not going to ask you to do like the super fancy mathematical stuff, but what I am going to ask you to do is ask you to go from code to this symbolism. Just like I've been asking you to go from the code to the code model before we hit recursion, I am going to ask that you can go from recursive code to fill out this recurrence. We will have plenty of practice. Also go to section on Thursday. That's all we're going to be talking about in section. Yes?
So for recursion, every constant matters, right? Which is different from before.
Sorry, say it again.
For recursion, every constant matters. So you always need to multiply it by n or something?
Ooh, good question. So in this recursive branch, do the constants matter? Because it's going to amplify over and over, right? Annoyingly, the constants still don't matter that much. They will ultimately drop away. And what you'll find is in this case, what we care the most about is, so like you could write this exact same recurrence. You could write this like some constant up here. So there's some constant amount of work in this. Then I do want to know the actual number of recursive calls. This is what matters, that coefficient of 2. What also matters is how n changes, because how n changes, that's really what's essentially our for loop header to dictate how we get from the top of the recursive stack down to the bottom. But then this constant stuff here, that doesn't really matter. So I could write that with like another C placeholder or something like that. Yes, good question. Yeah? Yes?
So the 2 in front of the t does matter?
So the 2 in front of the t does matter, and that 2 comes from how many recursive calls we've got. So I want to know number of calls. I want to know change of n. But other than that, the other stuff doesn't really matter. But do keep in mind that though the constants might like kind of not matter, for example, if I did have some work here that was like, I don't know, some constant, but in a factor of n, you can't let the n drop out. You know, maybe up here, this is like an n squared function or something. I don't care about the coefficient, but I do care about the factor of n. Yes?
Wait, so when you're analyzing like the asymptotic analysis, is it like a addition and you drop it?
Ooh, good question. You're trying to get, how do we get from this to asymptotic analysis? That's where your brain's going, right? Yes, because previously our brains almost went to asymptotic analysis before I could stop them from doing it, right? You just like could see what the biggest factor of n was, and you're like, there's an n squared in this quadratic equation. It must be an n squared. Great question. We're going to get to it in the slide. Just to feel more comfortable in terms of a recurrence, why don't y'all take a couple minutes right now and try and write a recurrence for this code that you see on the screen. Go ahead. So remember, I want something that's t of n equals base case recursive. Yeah. Let me say like when n something. Maybe I will try to make this actually clean. Here, you talk and I will write these notes out. Something like that. And then this will be like else. That. So this helps. Okay. This is good. Okay. All right. Unfortunately, in the interest of time, we may need to press on. So when I'm writing a recurrence, I am afraid of the recursive parts, and I save those for last, usually. So let's maybe start with the base case portions. So remember, this up here is the base case, meaning this is all of the comparisons and work, and then ultimately the return that's going to happen that will prevent us from ever stepping into the scenario of calling a recursive call. So what did people get for the overall sort of runtime of this? Anybody want to offer theirs? Anybody? Maybe I will say, is this a linear amount of work? Yeah. Ooh, interesting. Is this a constant amount of work? Yes. I think we all agree to that. Yes, agree. Yes, so this is a constant amount of work in that this isn't creating a loop. It's just not looking over n. There's like, I would maybe say this is one, something like that. So like you end up with something that's like 2. I don't really care what this number is as long as it's something that's constant. And so then you can imagine a best case scenario is a situation in which like this recursive function never triggers a recursive call. We just hit that base case over and over and over again, whatever's happening. Chances are that's not going to happen because the other thing we need to know is when the base case occurs. So when does the base case occur in this situation? Less than 3. You're absolutely right. So if I've got my t of n here, maybe I've got like 2 when n is less than 3. Boom, I've just filled out my first branch. Okay, now diving into my recursive branch, let's talk about the non-recursive work first. So I see I've got a for loop here. How many times does this for loop iterate? N. I agree. So this is like, maybe this is like one item in here and it runs n times. So there's some n work there. And then if I come down here, I see like maybe there's some extra non-recursive work, like maybe that's a +2 or something there. So we know that there's some amount of recursive work, but then plus it's got like n +2 or something like that, kind of hanging off the edge of it. Now we're finally at the part where we need to do the confusing thing. How many recursive calls are we going to make? 2. I agree. How am I going to represent these here? What do I put in between the parentheses of my t? N over 3, yes. It's almost like I did this intentionally to make this one a little kinder to you. Yes. There we go. Okay, apparently you can go look through all of the actual animations on this, but there you can see, yeah, that looks pretty much exactly like what I wrote, except I maybe like left off that little constant or whatever there. Yes?
I know this doesn't matter for like asymptotic analysis, but when you do like the int val1 is equal to recursive function, does it run each time you recurse? So like, would that be inside the n plus?
Ooh, good question. The question is about this work here. Yeah, so that I would say is probably technically counts in like this bucket of non-recursive work. So I would say if you wanted to then, like, and look, I even apparently left it off of this because I just didn't care. So maybe that's like +1 there and that's +1 there. So maybe this is really plus n plus 4 or something like that. But it's the lower order term, and apparently I just decided I didn't care or didn't bother to animate it in here. Questions on how I got to this recurrence? Okay. I am going to attempt in the next 6 minutes to get through the rest of these slides. Oh, yes, please.
So did you need to put that +4 into the non-recursive column?
That +4 that I just wrote and then erased? You don't need it. That's why I just apparently left it off the slides and then erased it. But just in case you were curious where it was coming from, it was like these two pieces of this two piece. It just is going to drop away in asymptotic analysis. That's why I left it off. But I did need to include this n because that was a whole factor of n. So for example, if that n wasn't in here, I could maybe leave this as like, you know, like plus some constant or something like that. But that n is something that I do need to account for. Now, to answer the question about what the heck do we do with this thing? Now we've got it all nice and mathematically represented. How the heck do we actually get asymptotic analysis? How do we get big O, big omega out of this? It's really hard to do that just by looking at it. So a bunch of really smart mathy humans out there created a theorem where you could just plug and chug. Heck yes. Thank you, math humans. So if you have a recurrence in this form, not all recurrences can use the magic that is the master theorem. We're really clever with the naming of these things. So master theorem is specifically a plug and chug to get the big O analysis out, and specifically to give you the big theta analysis. So it will give you thetas if you have something in this format. So here you can see that you kind of have to map the values to certain letters. So the base case work, that's D. The coefficient of the recursive cases, that's A. The way that N changes, that's B. And then any extra non-recursive work that's part of the recursive call, that's F of N. So the way that you can plug and chug this here is you can see log base B of A, whether it is equal to or greater than C. And I just realized that, did I leave C off? Yeah, sorry. What this actually is, and maybe I will change these slides, C equals the exponent of N for the factor in F of N. So in this case here, why? In this case here, the really crazy, annoyingly confusing thing about it, and I'll go back and make this clear on the slides, is technically there's like a little 1 exponent there because n to the 1 is n. So C in this case is 1. C equals the like exponent of biggest factor of n. So for example, if this instead, if f of n was n squared, C would be 2. If f of n was n cubed, C would be 3. So we've got an A of 2 coming from here, a B of 3 coming from that reduction there, and C coming from this silent 1 exponent here. So it turns out log base 3 is equal, oh yeah, here's this log identity to help you figure this out. Log base 3 of 2, set that equal to x, solve it out. You can see what the actual number is. I'm going to be real. I just plug it into Wolfram alpha, get it. And then you can see, in this case, it's less than 1. So we end up with a theta of n. Plug and chug. Now, let me see. I know we're taking notes, but real quick. Here is an explanation of why this actually does make sense. And it really does kind of break down to what percentage of work is being done before you recurse versus what percentage of work is doing right at the recursion or after the recursion. That's really what's kind of happening here. So they did a bunch of stuff. You can read through this. We are going to, you know what? Maybe we will just, let's see. We have to do heaps on Wednesday. Okay. We will talk about some stuff on Wednesday for this final pattern. And so for my last 30 seconds, let me talk about this slide for a little bit. So in this case, where A is less than C, which is exactly what we have here, what's happening is you can see that we actually have a lot of non-recursive work that we're doing. It's coming from this. Anytime you end up with a pretty big amount of non-recursive work that's happening in the recursive case, that's pretty much where you end up with these sort of higher order runtimes. Because then, as you can imagine, every time you recurse, you're incurring all that extra expensive work. It's very different from, say, I'm doing a lot in the base case, but like my recursive case, I just split until I get down. I'll leave it there. I'll talk more about it, I think, on Wednesday. We'll do some very brief tree method. And I aspired to make this one lecture, but I guess it'll be 1.25. It's fine. All right. Thanks so much, everybody, for being here. We'll see you Wednesday.